So let us start. Today, I'm hoping it will not be 1.5 hours lecture. I'm hoping it will be less because there is no. Basically, my idea is that I want to wrap up the discussion on the sampling part. Uh, Basically, last lecture we talked about Metropolis algorithm. Today, we want to talk about Metropolis testing, and then an unadjusted Langevin dynamics. There is one sampler for that. We'll do that, and then we will kind of will stop because I can go to the next topic, which will be then score based model, but that will then I will not be able to complete it today, or not even complete a section of that today. So that's why my idea is that we will just do Metropolis testing algorithm and then do the unadjusted Langevin dynamics and kind of stop and maybe give you some overview about other Markov chain Monte Carlo that are uh, there. So that is kind of the plan for today. So I'm hoping that it will be a shorter lecture as opposed to what we usually have. And today I had said that I might cancel the lecture, but I did not. I sent an email, right? As a consequence of that, now I am saying that I might cancel the lecture on Tuesday because whatever I had today has moved to Tuesday. Okay. But we'll see about that. I might not also. Okay. So anyways, if I cancel, you will get an email. If I do not cancel, you will also get an email. So don't go by that. Practical 2 is due on Monday, I guess, or something like that, Tuesday. So yeah, please complete it and upload it. Practical 2 or 3? 3, right? Yeah, 3. Sorry, 3. Practical 4, I have asked Subankar, who is a TA, to make that. So he will make that. That will be mostly on energy-based model and Markov chain Monte Carlo. And that will be provided to you on Monday or before that. Okay. Report 2 will be due next week, Friday, for the project. Okay. So that will be due next week, Friday. I will create that link. And yeah, those are all the updates I wanted to give you. Okay. So with that, let us start. And this is basically a review of what we did last time. Top left, what you are seeing, what is that? Top left? I see some mistake there, but yeah, P is the transition kernel, keep that in mind. P is not a probability, top left. So that is basically your pi invariance. We talked about pi invariance, it is that pi invariance criteria, right? Where P is my transition kernel, I mean, in our notation, we're writing it as K. So P is basically K. We're using P for transition matrix and K for transition kernel, so you can, but in this case, it is transition kernel. And so that is the pi invariance criteria, right? And then pi invariance is not enough. There are two additional criteria, which are the aperiodicity and irreducibility. Aperiodicity means that it should not be periodic, it is supposed to be random. Irreducibility means that no matter where you start, you should be able to go to all other states, including itself, in finite number of steps. Okay, or with finite probability. I mean, however we want to state that, right? And then one more thing we said was that it is very difficult to design a transition kernel that satisfies pi invariance. So basically, using pi invariance, it is very difficult to come up with a transition kernel, right? And therefore, because it is difficult to do so, what we have is the detailed balance criteria. Detailed balance criteria is also known as the reversibility criteria. I did not use that term last time, but it is also known as the reversibility criteria, and the idea is very simple. You are at x and you multiplying, so you are going to y is should be equal to you are at y, and then you are transitioning to x. That's why it's a reversibility, right? Pi of x, k of x comma y is equal to pi of y, k of y comma x. That means the probability with which you are at x multiplied by how you will transition from x to y. So that thing should be equal to you are at y, and how you will transition from y to x. That's because it's reversible, right? It's known as the reversibility criteria. Also, there is something on ergodicity as well. So when it converges, the behavior is ergodic, the statistics do not change. Uh, Again, something that we did not talk about. But yeah, not that essential, I will say. Lastly, one more thing I would like to say, that this sampling scheme, Metropolis algorithm that we discussed last time, allows you to draw samples from a chain, right? I drew that chain x1, x2, xn. So you will start from x0, and starting from there, you will draw a sample from x1, x2, x3, dot, xn plus 1, and so on and so forth, right? And remember, our criteria is that if we have designed a proper transition kernel, it will be pi invariant. So ultimately, the samples we will get will be from same distribution, right? However, it is not necessary that starting from the first step itself you start getting sample from the same distribution. You need some time before that pi invariance is in place, because you will start from some random initial sample. Because the initial sample is random, the convergence takes some time. And the time when it is getting converged, that is the time known as the burn-in period. It is known as the burn-in period. And you do not use the samples that you get during the burn-in period. How will you know what is the length of that burn-in period? Well, you just plot the samples you are getting, right? You will see that initially there will be some, if you take some average or whatever, right? Statistics, you will see the statistics will change for windows. But after a certain point, it will become stationary, and the statistics will not change, it will just fluctuate. So that is the point it has reached the stationary or pi invariance state, and from there you will start sampling. Okay. So there is a burn-in period. You should not use sample from the burn-in period, because that is where those samples are not from your target distribution, pi star, whatever you call it. And so those are like not useful samples. Okay. Uh, Theoretically, your chain only converges as n or t tends towards infinite. So the Markov chain only converges theoretically when t tends to infinite. But from a practical purpose, that infinite you can never use, obviously. So what you use is probably maybe the first 500 samples are burn in, for first 1000, maybe first 100, and that will be decided by that plot, the statistics plot or whatever the samples you are getting. Okay. Okay. So with that, finally we talked about the Metropolis algorithm, and that is what I have shown here as algorithm, right? The bottom one. What you are seeing here is that you have a target, you have a proposal and a target. Target is pi of x, proposal is q of y given x. It needs to be, what is the criteria for symmetric? It needs to be symmetric, right? So that q of y given x needs to be symmetric. So that is symmetric, we will assume that. And you will also have to give what is not written here, but the length of the chain you have to provide. And once that is provided, you start this chain, sample from the proposal, calculate the acceptance ratio, and then based on the acceptance ratio and you either accept or reject, right? I have not shown here, but there is a if criteria. If u sample from u0 to 1 is less than the acceptance ratio, then you accept, otherwise you reject. So that combiningly I have written in this manner, right? This is the Metropolis algorithm. What is the one limitation of Metropolis algorithm? There are many actually, but one major limitation is that you are restricted by symmetric proposal, right? I said there are many. So what do I mean when I say there are many? Well, the convergence takes time. Initial samples you cannot use, so that means it is slow. Acceptance ratio, generally the optimal acceptance ratio is between 0.28 to 0.4. You can understand majority of the samples are going to be rejected, and how to arrive at that number itself might be challenging. And that you will decide based on the proposal you select. So what is a good proposal, that itself is a challenge, and so on and so forth. So we'll touch upon these aspects slightly as we move ahead. But the agenda for today, the main agenda for today, is to talk about how Hastings modified the Metropolis algorithm, and so we call it Metropolis Hastings algorithm, to allow us to use proposals that are not symmetric, allow us to use generic proposals. So that is kind of the idea for today, right? Primarily. Okay. But before I start with the Metropolis Hastings algorithm, let me first talk about the burn-in period with a diagram. I talked about it, but I did not draw the diagram. So maybe the burn-in period is an important concept. So let me talk about it, right? So since we start from random sample initially, the samples run during the initial steps are not from the target distribution, which naturally means, so because of this, we do not use this samples, right? And this period is known as, this is known as burn in period. Okay. So let me kind of draw it. So when you start drawing samples, let's say this is the chain length, let's call it n, and this is basically the y-axis is basically the sample. So initially what you will get is probably, this is what you will get. You can realize that the samples are random. The fluctuations can vary based on the standard deviation of the distribution you are trying to sample from. But the initial phase, you can see that is not stationary. The statistics are changing, right? Initial time. So this sample, this is samples during this period. So let's say this is your potential burn-in period. Right? And beyond that, the statistics is not changing, it's stationary. When I say statistics is not changing, what do I mean? Take a small window, you have samples, calculate the statistics of that. Now keep on sliding that window. You will get statistics differently for each window. They will kind of not change, and that is obvious from this diagram itself, right? So you need to plot this diagram and decide what is your burn-in period. And in that burn-in period, whatever samples you are getting, that has not converged. The chain has not converged, which means you should not use that. I mean, theoretically, the chain never converges. It converges at infinite. But when I'm saying the chain has not converged, I'm talking from a practical point of view. Okay, not from a theoretical point of view. Theoretical point of view, it only converges at t tends to infinite. Okay, and you will never reach infinite. So infinite is a big number for you practically. So what that big number is problem dependent. Number of samples and the sample values. Each time you will get a sample, right? And so that's all. Okay. Clear? Okay. So with now this being done, let us proceed to the Metropolis Hastings algorithm. Metropolis Hastings algorithm. This is known as MH. You will see many places you will see MH MCMC. That means Metropolis Hastings based MCMC. Okay. As I said, MCMC is a broader family of sampling schemes which follows the concept of Markov chain. Metropolis Hastings, Metropolis, these are very specific algorithms that uses the Markov chain concept, but that does not mean that is the only Markov chain based sampling scheme, right? Okay. So for Metropolis algorithm, we will do the following. First and foremost, I will write down the Metropolis algorithm. So I'll write all the steps of Metropolis algorithm. Then we will go back and make changes in that algorithm, maybe in a different color, to show you categorically what was the change that Hastings carried out to go from Metropolis algorithm to Metropolis Hastings algorithm. And the changes are really minor. Okay. So that is what we will do. So let us first write down the Metropolis algorithm itself. And you will help me, obviously. Okay. So you will be helping me. So although it is written Metropolis Hastings, I am actually writing Metropolis, right? What is step 1? What are the inputs? Let me put it that way. What are the ingredients you need for using Metropolis algorithm? Length of chain, proposal, which is Q, Y given X, and this needs to be symmetric. So I'll write that as well, because ultimately you know that it will not be symmetric for Metropolis Hastings, right? Anything else? Normalized or unnormalized? It need not be normalized. So target distribution, as someone was saying. Target, which is pi, let's say of X. Anything else? Starting point. So let's say X naught. This is all right. These are the things that you need to start your Metropolis algorithm, correct? And then what is the next step? No, first you have to start the chain for loop, right? So for I or small n, whatever, let's write t is what we're writing, t equal to 0 to n minus 1, right? That's what we're writing. You will sample y from q of y given xt. You will parallelly sample u from uniform of 0 to 1, right? Next step, calculate the acceptance ratio of going from xt to y, right? So next you will calculate a going from, you are at xt, you want to go to y. And how do you calculate it? minimum of 1 comma pi of y, right, divided by pi of xt, right. You will do that. What is the next step? You now compare u with at or axt comma y, and that based on that comparison you will decide what will be your next sample, right. So let us use the next page. So next is you will compare if u is less than a x t to y, then your x t plus 1 will become equal to y with probability a x t comma y, right. Else x t plus 1 is equal to x t with probability 1 minus a x t comma y. This was the algorithm that we discussed last time, right? Nothing new. There are two changes we will do, just two changes, and one changes you might have noticed I left some space, so you know where the change will come, the magic. So let us see. What is the first change? Exactly. It is now not a requirement. You don't need it to be symmetric now, right? The second change is actually more subtle. Second change is here you multiply it by q of x t given y, q of y given. So what do you do? You do two things. You change your acceptance ratio, and acceptance ratio is now also function of the proposal, and this allows you to now use any proposal without the constraint of it being symmetric. Okay. Now let us do one quick sanity check, that what will happen if my q of whatever q I am using is symmetric. What does it mean? Q of y given xt will be equal to q of xt given y. Correct? So look at that black term, they will cancel out and you will go back to the original Metropolis algorithm. So looks correct. I mean, intuition is saying that okay, Metropolis is now becoming a special case of my Metropolis Hastings algorithm, right? That's the intuition we are getting. And that is quite clear that okay, if it is symmetric, I can exchange x and y. Let us put that here. The black term, the new terms are getting cancelled out, and we are getting back the acceptance ratio that we use in Metropolis algorithm, right? Now think, this is a very small change, right? Correct? But this took 20 years. Metropolis algorithm was proposed in 1950. This was proposed in 1971 or something like that. 1970s, let's put it that way. 70, 71, 72, somewhere around that. So someone told me in some other context that the life always looks clearer in the rear view mirror. So because it is done now, it seems like it is very simple, but unless it is done, it was not so simple, because you need to come up with that idea that, okay, we can even do that. You first need to think that, okay, this is actually a constraint. Then you need to think, okay, if it is a constraint, how to address those. And then you have to come up with some proposal, which was this one. But ultimately, there was a 20 years gap between Metropolis algorithm being proposed and the Metropolis Hastings algorithm being proposed. There's a 50 years gap between Markov chain being proposed and Metropolis algorithm being proposed, which is still okay, because Markov chain to Metropolis was not, even now it will not seem trivial, right? But Metropolis to Metropolis Hastings might seem very trivial. It is trivial when you look at it now. But think about you sitting in 1960s. This is not known. At that time, this might not be so trivial. So sometimes the answers you are searching for may be much easier than what you are looking at. You are probably making it over complex, right? Okay. So this is your Metropolis Hastings algorithm. Hmm. A. Very good. So that's the next thing we'll do. We'll prove that this also satisfies the detailed balance condition. Exactly. Now, not only detailed balance, we need to discuss all three conditions. So that's why I said that let me first write down the algorithm, and then let us have a look that does it now satisfy all the three conditions. If it does not, then there is some problem. But it is very unlikely. If it does not, that means I am making mistake, because obviously they have proved it already. So if I now cannot prove it, that means that is my mistake, not Hastings' mistake, obviously, right? Because this is proven that this will satisfy that. Scientist, scientist. Hastings is who proposed it. So in that case, is Gaussian symmetric depends. I mean, how you are representing your mean and covariance. So it depends on how you are representing your, because it is y given x, right? If you take xt as your mean, then it is symmetric. But if you take xt plus alpha as your mean, then it is not symmetric. Correct? So it depends that what are you taking as your. So Gaussian does not guarantee it is symmetric. It's how you are representing it that will decide whether it is symmetric or not. Okay. So now, as correctly pointed out, right? So this is the Metropolis Hastings algorithm. So what is the transition kernel, first of all, which will remain same more or less, only A will change. And does it satisfy the three conditions that we talked about in our last lecture? These are the two things we need to first discuss. And then we need to discuss what is the proposal, what are the proposals we can use. Because right now, whatever we have discussed is based on some arbitrary generalized proposal distribution. But it is not necessary that uh, we need not keep it generalized. There will be some good proposals, some bad proposals. So we need to discuss about that as well. Okay. So with that, let us first write down the transition kernel for this, right? Transition kernel for Metropolis Hastings, right? Uh, Remind me or tell me, not remind me, what is the transition kernel for Metropolis Hastings? Uh, K xt comma xt plus 1 is equal to hmm, is equal to first First, you have to sample it. You will sample it from where? Q. Q of what? Q of what? Xt plus 1 given xt, and then multiplied by acceptance ratio, right? So let me write down the acceptance ratio in the actual form, right? So acceptance ratio is, in this case, minimum of 1 comma not y, xt plus 1 by phi of xt multiplied by q of xt given xt plus 1, right? Divided by q of xt plus 1 given xt. Okay. This is the first term. This represents the scenario when your y is accepted, correct? But there is one more scenario where y is rejected, and that will look something like plus integration of q of y given xt multiplied by 1 minus of, we'll write, don't write, in this case we don't need to write the actual formula, we'll write a, because you know this case will not need that. A going from xt to y and then dy, right? Remind me why the integration in the second case and not in the first case? Multiple y's, for multiple y's your samples can get rejected, and that will result in xt plus 1 is equal to xt. So it is representing that scenario, right? One more thing is that just simple question. Under what circumstances xt plus 1 will become equal to xt? Can you think of under what circumstances xt plus 1 will become equal to xt? You can look into the algorithm, obviously. Hmm? If acceptance ratio is less than u, then xt plus 1 will be equal to xt, right? But is there any other case when it can happen? That is one case. When xt plus 1 will become xt is when y is rejected. But there is one more case when xt plus 1 will become xt. What if the sample you drew come out to be xt? In that case, acceptance ratio will be equal to 1. That will be accepted definitely. But that is not normal. It will not happen very often. But that's a possibility, right? You can also get xt plus 1 equal to xt if qy given x, the y you got is equal to xt. That's possible. Not likely maybe, but possible. Right? So even in that case, xt plus 1 can be equal to xt. But that case is already absorbed in the first term. So we need not worry about that. In that case, xt plus 1 will automatically be xt, and that's okay. That is absorbed. We are only accounting for the facts where y is rejected and xt plus 1 is equal to xt. And that is the term that the second term is representing. And this is true for metropolis as well. This is not only for. Any question? This is clear? Okay. Now, why it is irreducible? Why it is aperiodic? Let's start with aperiodicity. Why it is aperiodic? Simulate. Exactly. similar to Metropolis algorithm, a sample can be rejected with a finite probability, which means even if the proposal somehow give you periodic kind of sample, sometime it will be accepted, sometime it will be rejected, and that's with a probability, so it becomes random variable, aperiodic, right? In that irreducibility, how do you ensure irreducibility? By selecting a proper Q. I mean, that's all you can do. Okay, by selecting a proper Q, proper standard deviation. So Q means it will have some standard deviation. So by selecting a proper Q, you make it irreducible. And this too is the same, exactly same as Metropolis algorithm. With last time we talked about, if you take a Gaussian, there is a finite probability from any sample, you can go to any other sample, that means it is irreducible. So last time we talked about it. I said if you take a proper proposal with a proper standard deviation, it's irreducible. How do we know? Uh, Theoretically or in practice? Theoretically, it is very simple, right? If you know your original distribution is uniform, right? And you take, let's say, a proposal that covers A to B, then it's irreducible. It can go to any points in A to B. Gaussian to anyways goes from minus infinity to plus infinity, so that anyways is valid. Right? So in that sense, okay. Now the important one, the little bit involved one, which is the detailed balance. How do you satisfy the detailed balance? We will follow the exact same procedure as last time and see whether detailed balance is satisfied or not. Okay, so let us look at rejection is probabilistic. You are drawing U from a you are drawing U from a U is drawn from where? This is a U, right? The U is drawn from where? Uniform. And uniform is what? U is periodic or U is random? If U is random, how can rejection be periodic? Periodic, what do you mean by one case is periodic? What is periodicity? So can you say looking at one sample it is following a pattern or not? I will give you sin x one value, x at x equal to 0, y equal to 0. From that, can you say that it is coming from sin x and hence it is periodic? You need at least multiple u. So these multiple u's are from random. So how can it be periodic? When there is a when I'm saying there is a concept of A is a probability, that means it's random. Something random cannot be periodic. Random means it's an experiment, the outcome of which is not known a priori. If it's periodic, the outcome is known a priori. It is sin x or cos x or whatever, a combination of that, right? Clear? Okay. So the question that we will now answer is, does Metropolis's thing kernel satisfies detailed balance, okay, which is dB. So first let us write down the detailed balance condition. Remind me what is the detailed balance condition? Phi of xt, then k of xt comma x t plus 1 is equal to phi of x t plus 1 k of x t plus 1 comma x. Okay, this is what we need to prove. We'll start with the left hand side as usual and proceed. So from LHS, what do we have? Pi of xt multiplied by k, right? And let's write down the k. The k is equal to q of x t plus 1 given xt multiplied by minimum of 1 comma pi of x t plus 1 pi of x t q of x t given x t plus 1 q of x t plus 1 given x t, and this is my first term, right? Correct? And we called it what, a t or something like that last time we were calling it, right? Let us also write down the second term. The second term is plus pi of x t integration of q of y given x t multiplied by 1 minus a x t comma y dy, right? Correct? I hope I'm not missing anything. Okay, right? So now the second term represents what? The second term, which is in what color, orange or whatever the color is, it represents what? The rejection. And in the case of rejection, xt plus 1 is equal to xt, right? So we'll just substitute that, right? So this represents rejection, which fundamentally means x t plus 1 is equal to x t. So wherever there is x t plus 1, I can go ahead and put x t. Okay? And so it's basically the exact same step as the last time, nothing changes. And you can guess that what will change is in the first term, because in the first term we used the condition that it is symmetric last time to prove it. Now we cannot use that. So first term. So let us focus on the first term, right? We focus on the first term. So in this case, what do we have? What is the first term? Remind me. Pi of xt q of x t plus 1 given xt multiplied by minimum of 1 comma pi of x t plus 1 by pi of xt multiplied by q of x t given x t plus 1 given q of x t plus 1 given x t. Now last time what did you do? Last time what was the next step? We pushed pi of xt inside the minima, right? That's what we did last time. What will you do this time? Push both the terms inside. both the terms will push inside instead of only pi. So let us push both the terms inside the bracket. So this is equal to what? This is equal to minimum of the first term will become whatever was outside. So pi of xt q of x t plus 1 given xt, comma, what will be the second term? The denominator gets cancelled out. So only the numerator remains. Pi of x t plus 1 q of x t given x t plus 1. Right? Next, what will I do? Should be able to tell me. The second term I will now bring outside. So let us bring the second term outside. This is equal to pi of x t plus 1. If I don't prove it from here onwards, I am sure most of you will be able to now prove it. There is nothing new now, right? And then minimum of pi of xt divided by pi of x t plus 1 q of x t plus 1 given xt divided by q of xt given xt plus 1 comma 1. This minima term, what is it? You know this minima term. What is this? A of x t plus 1 comma xt, right? It is a of x t plus 1 comma xt. It is the acceptance ratio of going from x t plus 1 to, right? So now if I call it, let's say, equation 1, right? This one as equation 2, this one as equation 3, and this one as equation 4. I can substitute equation 4 and equation 3 into equation 2, right? Equation 4 into the first part of equation 2 and equation 3 into the second part of equation 2, correct? Let us we substitute that. Substituting equation 4 into first part of equation 2 and equation 3 into the second part, we get, what do we get? Pi of x t plus 1 multiplied by q of x t given x t plus 1 minimum of pi of x t by pi of x t plus 1 q of x t plus 1 given x t q of x t given x t plus 1 comma 1, which is basically my a of x t plus 1 comma x t plus, for the second term I get q of y given x t will become x t plus 1 and then 1 minus A x t plus 1 comma y, right, dy, which is basically equal to pi of x t plus 1 multiplied by k x t plus 1 to x t, which basically proves, so basically the detailed balance condition is proved. Clear? It is simple actually. If you know the trick that what has to be proved, and if you know the observation that okay, for the second part xt plus 1 is equal to xt, it's not that difficult. But remember, it's work of 20 years. I mean, not work of 20 years, but it took 20 years to arrive at this. I mean, I don't know how many years Hastings devoted for that. But we do know that by the time it came out, it was 20 years from the original level. That we know, right? Any question? Intuition is that the detailed balance is satisfied. It is getting cancelled out. That is the exact intuition, right? The detail, because you have to ultimately satisfy the detailed balance. It was not getting satisfied with the acceptances we had. And the reason was Q was somehow not getting reversed. So the intuition is that now whatever was there, put it in the denominator, and the opposite put it in the numerator. It will get cancelled out and it will come out. So the proof came before the algorithm, right? I am doing it in the opposite manner, but originally the proof came first, the algorithm came later, right? So what are the conditions for it to be a metropolis, for it being a Markov chain Monte Carlo? The condition is that whatever you take proposal, whatever you take acceptance ratio, basically whatever you take transition kernel to satisfy detailed balance, irreducibility, aperiodicity. Aperiodicity and irreducibility are trivially satisfied, more or less. Detailed balance is where the symmetric condition was needed. So what can we change in the detailed balance criteria so that the symmetric condition goes away? And once you have done that, now that comes to the algorithm, right? Okay. Any question? If there is no question, let us move ahead and talk about possible proposals. What? Okay. There is dy, so that should be integration. So right. I mean, the dy is there, so the integration definitely is there. So I have just missed it. Obviously, right? Okay. Okay. So the next part is very briefly proposals. Okay. So the most common proposal is, I talked about it last time very shortly, is random walk. And random walk proposal takes the following form. So the first one is random walk. And this one is q of x, or maybe I should write y, given xt is a Gaussian over y with xt as mean and some standard deviation which you have to select. Okay, and this standard deviation selection controls your convergence, and exploration versus exploitation kind of balance is determined by the sigma square. If it is very large, that means you are actually encouraging exploration. Whereas if it is very small, you are saying that okay, I got a good sample, I will just look around that. So it's a exploration versus exploitation kind of trade-off. Okay, so this basically means this random walk basically is equal to basically that this implies y is equal to xt plus epsilon, where epsilon is from a Gaussian with 0 comma sigma square, right? This is what it means. And that's why I said it was motivated from how a drunken person walks. So you are at a given position, and from there randomly you can go anywhere, including staying in that position. So that's from where it is kind of motivated. This will be symmetric, right? More or less. I mean, xt given y will be equal to, because that's the mean. So you can, yeah. Okay, so this is the random walk proposal. Most popular one, but sigma square tuning is a headache. You can have different ways of tuning sigma square and so on and so forth. But yeah, okay. And one important thing is that remember that with this kind of setup, right, your proposal is actually getting changed in each step, because your proposal is function of xt. So it's function of what sample you drew in the previous step. If your sample changes, your mean changes. If your mean changes, your distribution changes. You can as well change your sigma square also. You can make it adaptive and all of those things. That's fine. But the original one does not do that. So they kept sigma square same, but the xt changes, which means the distribution changes. It's Gaussian, but it changes. Hmm? Louder. You can, because yes, but it's a metropolis testing. What is the problem with that? We don't need symmetric. You can use whatever proposal distribution you want. There is no restriction on that, right? That is the whole idea of this whole thing, right? So this is known as random walk metropolis testing. There is also something known as independent metropolis testing. So in independent, the proposal does not change. So you take some constant independent proposal and you retain that. It will not change sample to sample. The problem with that is now the irreducibility condition is trickier. Now the irreducibility condition is trickier because now that initial sample, whatever you are taking, should cover the whole, because it will not change now. In this case, the advantage is that because even if sigma is very small, because x is changing, this can shift, and by shifting it can probably cover the whole space. But if you keep it fixed, then it should be very big and encompass the original distribution, right? So that is the idea. Any question? If you take some, it is having some mu, yeah. Yeah. Your what is original distribution here? Again, what is original distribution? You have to explain. There is no original distribution. What? Where are you seeing pi here? Do you see any pi here? Is there any pi in this expression? Is xt getting sample from pi at the beginning? Xt equal to 0. So then what is original distribution here? There is no original. The acceptance ratio will decide whether you are accepting or not. And the acceptance ratio will take care of that. There is nothing original here. So what original are you talking about? No, it's not. It's not. Y is some random sample drawn from the proposal. Right? It's a proposal distribution, not your transition kernel, not your target distribution. Keep that in mind. Okay. Clear with this one? Independent sampling, independent Markov chain, or what you do is that you have a constant kind of, let's say, Gaussian or whatever, but that should supersede your original distribution. Why supersede? So let me also draw it. The next one is independent, right? So in that case, q of y given x will be equal to q of y. You can imagine, let's say now this is your target. Let's say your target distribution is this. Let's say this is my target distribution. So you now, if this is my target distribution, my proposal should supersede this distribution. Only then I can ensure that I will get sample from everywhere which is having a non-zero density. If my proposal, just assume, if my proposal becomes something like this, then I will never get any sample in this position. I will probably not get sample in this position, which are actually valid samples. The chain becomes reducible. To make the chain irreducible, which means that the samples you should be able to draw from all possible locations which have non-zero probability density. To ensure that, you need a proposal in this case which supersedes the target distribution, right? Yes, so that's why random walk is preferred over this one. Yes, this is actually used in rejection sampling. In rejection sampling. No, non-zero. Any position where the original target is non-zero, this will also be non-zero. That's all it means. It can go through in between also, but that's okay. Very difficult. You don't know the distribution to start with. How will you even know? That is why independent is never used. Whereas in random walk, because it is walking slowly, you are fine. You can adjust your sigma and it will kind of work. Right? Any question? What is this? Independent, because what is definition of independent? It is q of y given x equal to q of y. So it does not depend on x. It does not depend on what sample you drew earlier. The original definition of independent. Never. I've never not seen any place where you will use it. Unless and until you are too lazy. Or maybe in homework or an assignment. That can be another place I can think of. Otherwise, no, nowhere. Okay. Going to, let us proceed to some more advanced kind of proposal. There is something known as nice MC. In nice MC, I think the original paper trained a GAN model and used the GAN model as a proposal. You have a GAN model, you draw sample from that GAN model, and that is your proposal. And now you accept or reject based on that. So that paper came out in 2018 or 19, known as nice MC, and search for it. No. GAN, they use GAN. Why they call it nice, I forgot. Actually, okay. Yeah, so look at it. But that's a good paper actually. But for that, remember, you need data a priori. I mean, you first need to train a generative model based on data, and then only you can use it. Whereas this actually is data free. You do not need any data for this. This is just sampling. You know, just normalized distribution, unnormalized distribution, you can sample. Okay. There is also something known as Hamiltonian Monte Carlo. I will not cover it this time. I covered it last time. So you can check it. So there you use the principles of Hamiltonian and how particles move following while conserving energy. So you use leapfrog algorithm, which is a symplectic algorithm, time integrator, and you draw sample, and those samples from your Hamiltonian, solving the Hamiltonian becomes your proposal. So that is known as the Hamiltonian Monte Carlo, or HMC. Okay, I think those who did reliability must have done it in one of the homework I gave, right? So that is known as the leapfrog algorithm. Okay, nice MC. Okay. Lastly, in the context of energy model, again, it is not for energy model, you can use it anyways. But in the context of energy model, what is mostly used is actually not metropolis testing. It's rather is known as unadjusted Langevin dynamics. Now, unadjusted Langevin dynamics is a metropolis testing algorithm with a very specific proposal. Okay. And there are two variants, one is unadjusted, one is adjusted. In unadjusted, you accept all samples. So acceptance ratio is equal to 1. In adjusted, there is this acceptance ratio business comes into picture, and you might reject samples. So there is the unadjusted and then adjusted. You just write down the proposal or transition for unadjusted. Everything else remains the same. Subhankar, you should use include unadjusted and adjusted in your practical. In this case, what you do is that it is very intuitive actually. Xt plus 1 is equal to xt plus epsilon times gradient with respect to x f theta of x, and f theta means this f is energy based model, the energy. Okay, as I said, it is evaluated at x equal to xt plus square root of 2 epsilon z, where z is drawn from okay. It is a very small number. Now, can someone explain me the intuition behind that? What is it doing? And by the way, you sample from it and you accept it. There is nothing to be rejected here. Okay. Unadjusted. In adjusted, you can then apply accept reject over this xt plus 1. Then you make it y and then do accept reject. You are very close, but can you articulate it better? You are actually in the right thinking correctly, but you need to articulate it better. What information does gradient gives? Maxima and minima, right? Gradient descent, what does it give? The direction in which the gradient is reduced maximum, or not the gradient, I mean the minima, the direction of the minima, right? Correct? But this is gradient ascent. Forget the last term. This is gradient ascent. This means this is pushing x towards the area of maximum density, which is logical. You should draw more samples from the area of larger density. From mode, you should have more samples. That's why we call it mode. That's what the second term is doing, isn't it? Is it not? It's a gradient ascent. Plus, there is some noise you are adding so that you don't get stuck. So that is basically, this was exploitation. The third term is exploration. And this is guaranteed to converge when the chain length is infinite and epsilon goes towards 0. So in the limiting condition, when epsilon tends to 0 and the chain length goes towards infinite, this is guaranteed to give you samples from the target. Yes, not probably mass, but higher frequency, higher modes, higher frequency. Mass means you have to area, you have to integrate, right? So mass, but yes, your understanding is correct. What choice of word is probably wrong, right? Now, what was the main issue with energy based model? The partition function. What happens to partition function here? Because it is supposed to be gradient of the PDF, but it is gradient of the PDF with respect to x, not theta. I have written gradient with respect to x. When you take with respect to x, z is function of only theta. Gradient of z with theta with respect to x is 0. So that term vanishes. So this, and that also makes sense because gradient is like what? X2 minus x1 by delta x, I mean, or by delta h, I mean, probably, right? Which is like comparing two samples. Here you don't need to do comparison. And then gradient with respect to x is? Gradient of constant with respect to x is? Is it so? Is it like that? What is the expression in energy based model? You forgot the expression in energy based model. F theta is the energy, not the PDF. The PDF was what? Exponential of f theta by z theta. How do you get this? By taking log. This is log probability gradient. So when you take log probability, what do you get? F theta minus log of z theta. Take gradient with respect to x. What will you get? 0 for that term. This is f theta, not PDF. This is the energy, right? So the comparison is anyways happening in the gradient calculation, because gradient means comparing the two neighborhood point and see the difference, right? That's the first principle of gradient. So that is anyways happening, and that's why that z term is vanishing. Okay. This is the unadjusted Langevin, which is generally used in energy based model. The reason is that there is no headache of accepting and rejecting, and I mean there is nothing rejection, but why anyone did not think this one first? I have to ask Langevin. Was it doing? Because I don't know the answer. I have to also ask Metropolis. But at the same time, why did you not think about it? The reason is that always you will not be able to find gradient. Gradient calculation is expensive. Keep that in mind. Gradient calculation is expensive. We know automatic differentiation is expensive, right? So that is one of the reasons, obviously. Uh, okay. So this is the unadjusted. For adjusted, you can do this. So this is generally done. But keep in mind that this sampling business you are supposed to do in energy based model, both during inference and training. Why we need it during training? Because what is the contrastive divergence? Difference between the training sample and some sample. How will you get that some sample? Using this kind of scheme, which means training will become extremely expensive, to the extent it will probably not be practical, which means the homework problem, or not homework, assignment problem that Subhankar will make should be very low dimensional. Otherwise, it will not run on your computer and code when it is based on sampling. So in the next lecture, this is the last thing for today's lecture. At least 15 minutes early, I'm finishing. Oh, actually 5 minutes early, to be very honest. I should end at 7:20, not 7:30. So in the next lecture, which I don't know whether it will be next Tuesday or Friday, we'll look into energy-based model, but from an alternative perspective of something known as Stein score. There is someone known as Stein who came up with Stein score, and how you can use that score, concept of score, to train these models without the need of sampling. Because sampling is not scalable, so you need alternative ways that is scalable. We'll talk about score and how score can be used to train this model. And this score is actually what is used for diffusion as well. So this code, with score, we are almost halfway into diffusion. Okay, so we might need another 2-3 lectures for wrapping up energy plus score, that combination, before we go to the next topic. Okay. Okay.